Okay, for this lesson, we were looking at solving equations within linear systems, and we're looking at solving for x in matrix form, and also we're looking at expressing the solution as a linear combination of what we have around the columns that we have established for the system. And for the first problem, okay, we're looking at a system of equations in the variable terms x of 1, x of 2, x of 3. And we have for this first system, okay, we have x of 1 plus 2x of 2 plus 4x of 3 is equal to 1. And then we have the negative of x of 1 plus 2 times x of 3 is equal to 3. And also we have x of 1 plus x of 2 plus 3 times x of 3 is equal to 2. So there are two parts here we're looking at solving. So we're looking at solving the matrix equation translation for what we have in the system for x. And also we're looking at establishing at least a linear combination of the columns of A. Okay, and so these solutions will kind of go hand in hand. And for the first system, okay, so if we look at what we have here, so we have AX is equal to B. And for the coefficients of what we have for the x of 1 terms, is to go equation by equation. So you have 1, -1, and 1. And again, we did not have an x of 2 term in the second equation. And we have for the x of 2 coefficients, have 2, 0, 1. And then for the x of 3 term coefficients, we have 4, 2, and 3. And again, we have the general matrix setup for x. We have, again, a 3 by 1 matrix consisting of x of 1, x of 2, and x of 3. And we have for B, again, we have the 3 by 1 combination where we have 1, 3, and 2. So I'm just carrying over what I have with the coefficients. And again, we have 1, 3, 2 as the constants to which we have each equation respectively set equal. And again, so for AX is equal to B. And in terms of the combinations, so you're looking at x of 1 times a of 1 plus x of 2 times a of 2 plus x of 3 times a of 3 is equal to b. And this is the general setup of what we have for the linear combinations. But first things first, okay, looking at solving for x of 1, x of 2, and x of 3, taking the coefficients of A as well as the coefficients from matrix B, I have an augmented matrix, okay, which is going to be combining the terms from the 3 by 3 matrix from A with what I have from the 3 by 1 matrix in B and consolidating as a 3 by 4 matrix. So we got 1, 2, 4, 1, -1, 0, 2, 3, and 1, 1, 3, 2. And looking at solving and expressing at least in terms of row echelon form. Okay, so I want the first column to consist of 1, 0, and 0. So if I add R2 and R1, as well as take the last row and deduct the elements from the first row, so we have, while the first row remains fixed at 1, 2, 4, 1, we have with the second row, after adding the first row elements, okay, we have 0, 2, 6, 4. And for what we have for the third row, after deducting the first row elements, we have 0, -1, -1, and 1. And just looking at the diagonal pattern, so I have 1 in the upper left-hand corner. Next row, I want to have at least 0 and 1. Okay, and so I can make this 2 into a 1, and I can just take half of the second row values. And so we have taking half of 2, 6, and 4. I have following 0, I have the numbers 1, 3, and 2. Now we've got 1, 0, 1, and I want the third and last row to start out with 0, 0, and 1. So I can make this -1 at the front into a 0, and I can do this while keeping the 0 in front as it is. I'm going to interact R of 3 with R of 2 by adding together. So adding the second row elements to the last row. So I have 0, 0, 2, and 3. And again, I have in establishing the pattern 1, 0, 1, and then to 0, 0, and 1, this 2 that we have to follow. I'm going to transform that into a 1 by taking half of the last row. Okay, and so we have 0, 0, 1, and 3 halves. And so looking at what we have for this particular form, okay, so we have x of 3 is equal to 3 halves. And I have for x of 2, we have 2 minus 3 times x of 3. And we have for x of 1, and we have 1 minus 2 times x of 2 minus 4 times x of 3. And x of 3 is already known. Okay, and looking at back substitution, with x of 3 at 3 halves, x of 2 is going to be 2 minus 3 times x of 3. And with x of 3 at 3 halves, x of 2 is equal to minus 5 halves. And for x of 1, okay, now the x of 2 and x of 3 are known. And substituting negative 5 halves for x of 2 and 3 halves for x of 3, okay, it turns out that x of 1 is equal to 0. So for the numerical values, we have x of 1 equal to 0, x of 2 equal to negative 5 halves, and x of 3 equal to 3 halves. And so for the matrix display for the solution of x, okay, so you have x equal to the 3 by 1 matrix, x of 1, x of 2, and x of 3. And filling in the values, we have 0, negative 5 halves, and 3 halves. And in terms of the linear combinations, okay, again, we have only one solution for x of 1, x of 2, and x of 3. So there's only one solution to the system. And so just putting back, so again, x of 1 is at 0, x of 2 we have at negative 5 halves, x of 3 we have at 3 halves. And so for the combination, you have 0 times 1, negative 1, 1, minus 5 halves times the matrix consisting of 2, 0, 1, plus 3 halves times the matrix consisting of 4, 2, and 3 equal to B, which again we have in matrix form consisting of 1, 3, and 2. And that is going to be the only linear combination we have for this first system. Okay, now for the second equation system, okay, so we got x of 1 plus 2 times x of 2 plus 3x of 3 is equal to 1. Then we have 4x of 1 plus 5x of 2 plus 6x of 3 is equal to 3. And finally, we have 7x of 1 plus 8x of 2 plus 9x of 3 is equal to 6. So all the subscripted x terms are consisting of natural number coefficients. So there is no void in this one, unlike what we have with x of 2 from the second equation in the first system. And for what we have, again, just for ax is equal to b, taking the coefficients of the x of 1, x of 2, and x of 3 terms. So I had this 3 by 3 matrix. And for x, again, I have x of 1, x of 2, and x of 3. And for b, again, the first equation we had set equal to 0, the second equal to 3, the last equal to 6. And again, we had the general linear combination, x of 1 times a of 1. Again, a of 1 is going to have 1, 4, 7, plus whatever we get for x of 2 times a of 2, which will be the 3 by 1 matrix consisting of 2, 5, and 8. And then we have x of 3 times a of 3 with a of 3 at 3, 6, and 9. And we have is equal to b, which will be consisting of 0, 3, and 6. And taking the a coefficients and adjoining with the terms from b, I'm going to have, again, the augmented matrix to be a 3 by 4 arrangement, and setting things up where I can get this to where I can at least set it up where I can provide back substitution. And so looking at what we have here, so I want the first column to be 1, 0, 0, and transforming the 4 and the 7 respectively. We're going to take 4 times the first row and 7 times the first row from, again, the second and the third rows. So we have with the operations 4, 5, 6, 3 changes over to 0, negative 6, 0, negative 3, negative 6, and 3. R3 changes over to 0, negative 6, negative 12, and 6. And for the second row, I can change the negative 3 into a positive 1. And so I'm just going to take negative 1/3 times the second row and leave everything else untouched. Okay, so in this operation, okay, we have 0, 1, 2, and negative 1. And then just carrying over, so I have the diagonal array of 1, 0, 1, and I want the last row to consist of zero, at least 0, 0, and 1. And okay, so preserving the 0 at the front and changing the -6 to a 0, I can interact the third row with the second upon adding 6 times the second row to the third row. And doing so we have 0 plus 0, -6 plus 6, which is 0. And guess what? -12 plus 6 times 2 is going to be -12 plus 12. And that is going to go to 0. And 6 plus -6 is 0. So for what this means is that the last statement, okay, there's a void. However, we got left-hand side is 0, right-hand side is 0. And we got a free variable with x of 3. So we're going to end up with an infinite number of solutions. Thus, what will be an infinite number of linear combinations. And so just for what we have in this arrangement, so we have x of 1, that's going to be equal to -2x of 2 minus 3x of 3. And for x of 2, we'll have -1 minus 2x of 3. And again, we don't have a 1 in the last row to represent x of 3. And instead we got 0 is equal to 0. And if I had like trying to say 0 is equal to a non-zero value, we would not have any solution or linear combination whatsoever. But with this as a true statement, we got, again, an infinite number of solutions. X of 3 is free, and thus we can set x of 3 equal to t. And for x of 2, we have what's going to be -1 minus 2 times t. And for x of 1, so filling in -1 minus 2t for x of 2 and t for x of 3. Once we plug in and follow through, we have that x of 1 is equal to 2 plus t. So we have for our combination, we have that x of 1 is equal to 2 plus t, x of 2 is equal to -1 minus 2t, and we have x of 3 is equal to t. And so in matrix display, we'll have for x, again, that is going to be consisting of x of 1, x of 2, x of 3. And for the layout, the top row will be 2 plus t. Middle row, in representation of x of 2, we have -1 minus 2t. And for the last row, we have t. And again, going back to the linear combinations, okay, since I have an infinite number of solutions, I can have infinite numbers of linear combinations. And let's say that if I have t is equal to 0, okay, so like your x of 1 is 2 plus 0, which is 2. X of 2 is -1 minus 0, which is -1. And x of 3 is equal to 0. And if I plug back in, and we have like 2 times 1 for 7. Then I have -1 or plus -1 times 2, 5, 8. Then I have plus 0, 3, 6, 9 is equal to, again, from B, we have 0, 3, and 6. That is one combination. And if I had like another combination, say if I were to set t equal to 1 upon infinitely or among infinitely many other values, if I set x of 1 such that we have t equal to 1, so x of 1 is equal to 3, x of 2 is equal to -3, and we have x of 3 is equal to 1. And so we'll have like 3 minus 3 and plus 1, okay, for, again, the coefficients respectively 1, 4, 7, 2, 5, 8, and 3, 6, 9. And again, we have equal to b, which again consists of 0, 3, and 6. And so this is going to be yet another linear combination.